Well, good morning, everyone. It's a great honor to participate with you in this conference. I'll be presenting our paper on hybrid system for iron and manganese reduction from polluted water using adsorption and filtration, presented by myself. I'm Dr. Ola Munayeri. I'm associate professor at the Arab Academy for Science and Technology and Maritime Transportation in Cairo, Egypt. This will show the components of our presentation: introduction, literature review, materials and method, results in discussion, and then followed by a conclusion. As you all know, we are all facing a water scarcity problem. It's a worldwide problem, but it is also present in the Arab world. And as we see here, all the colors colored in red have a very stressful water scarcity issue. Egypt here is one of them. So that is why we are having many research focusing on the treatment of the available water, whether surface water, underground water, or so we can provide the water required for the people and for agriculture and for industry as well. But of course, we have already passed the scarcity problem. We are already in it, and today, the amount of water reaching per capita is around 600 meter cube per year per person. Egypt is one of the countries that relies very much on water from the River Nile. About 55.5 billion cubic meter is received from the River Nile, but this is not enough, and so we are receiving a small amount of rainwater. We have reuse of domestic wastewater being treated, and we are using most of it, and we have groundwater, but which is not much. So we are trying to increase our sources as much as possible, and also including researching for more techniques to enhance our water quality, especially that we have the Red Sea and the Red Sea and the Mediterranean, which are very saline water, with very high salinity levels, so it needs special treatment. But in this paper, we have focused on mainly on iron and manganese as heavy metals, which were detected in different places in Egypt. Of course, you know that the source of contamination could be organic pollutant coming from antibiotics, dyes, and could be inorganic coming from heavy metal disposal. Iron is a problem because it causes water turbidity due to its yellow color and could damage the plumbing system. Manganese also gives an unpleasant appearance and taste in water. In Egypt, it has been detected in Mariat Lake that there are different concentrations of heavy metals such as manganese, cobalt, nickel, copper, zinc, cadmium, and lead. There were many researchers in this area discovering such concentrations. Also in Matruh and Ismailia and Beni Suef, they detected in the groundwater concentrations of iron, lead, copper, cadmium, and zinc. And also in Monofei government, they found the presence of iron, manganese, and ammonia at high levels. The manganese levels reached from zero and reached up to 2.4 ppm, and around 44 samples were taken, and iron was also detected in concentrations that exceed the allowable standards in Egypt. So what are those standards? According to WHO, the limits of iron should be less than 0.3 ppm. Manganese should be less than 0.1 ppm. Egyptian authorities allow iron to be less than 0.3 ppm and manganese to be less than 0.4 ppm. Of course, as you know, there are many methods of treatment. It will depend on the size of the iron and what do we want to remove from the water. So we have physical, we have chemical treatment, we have ion exchange, we have osmosis, coagulation, phytoremediation, photolysis. All these studies are present. Adsorption is another technique which is used, but it is cost effective and it has proven to have positive applications in the removal of such heavy metals. But still, many further studies are required to explore the mechanism of removal at a certain point and cost and application at another point. Desalination is another technique also used using reverse osmosis and the membrane and nanofiltration. All these techniques are present in the treatment. The materials that could be used these days that we have examined is clay. Clay is inexpensive for us in Egypt. We have a lot of clay because we have the River Nile, and so we have clay is present in abundant amount, and it is considered to be a cheap or a low-cost material. And there has been some studies done in the 60s under pressures of 10 bars, and it was placed in such a setup, and it has proven to have capabilities of filtration. Clay, of course, this is the structure of, we have kaolinite, we have montmorillonite, we have vermiculite, and smectite. Each of these has its own structure and bonding, and depending on which of these would be better in the removal of heavy metals, this has been tested in our work. We also have ion exchange resin. This depends on the exchange of the cationic and anionic ions. Yani we are exchanging ions with, such as iron and manganese, and we are comparing the results using this material to the clay and see which is performing better concerning iron and manganese. There are many, quite some researches that have been done in Egypt to study the effect of clay, but most of the models done or experiments done were batch models. Only we have one here who has implemented a column test, and they studied different types of heavy metals such as chromium and nickel and cadmium and zinc and copper and lead. Some have tested iron as well. All right. So the aim of this research was mainly to eliminate iron and manganese from aqueous solution by choosing the suitable clay mineral and determine its performance against cation exchange resin concerning iron and manganese. Concerning the experimental setup, we had prepared this aluminum cylinder, all right, with with a cap at the bottom and the bottom and the top, and we allowed for flow of water or the preparation, the samples that we prepared from a tank at a height of about 1 meter. All right, under the tank was open to the air, so there was zero atmosphere. The pressure implemented was due to the difference in height. All right, and from inside we have these are the components of the cylinder we prepared from inside. So as we can see here, we have a filter paper, we have a ring. We don't want to allow water to flow outside of the ring under the pressure because we were studying, we were having a constant flow, but we were having different concentrations of magnesium and iron. We prepared the synthetic solution. We used distilled water, and we used this was the source of iron used, and we prepared iron and manganese. This is manganese and this is iron. And the concentrations of 2, 5, 10, 30, and 50 ppm were examined for both metals. So this was prepared in the lab. And then, as you can see here, this was the capsule where we have pores present to allow the flow of water, and we have a filter paper, and we have a ring to control the flow and allow the flow of water without and checking the maximum retained amount concentrations of iron and manganese. These are the dimensions of the holes and the design of it. And as we can see here, also there was a ring also to maintain the filter or the media in its place, so as not to move during the experiment. And this was the clay element we got from Dar es Salaam. We got a clay from borehole test. It was the montmorillonite, and it was examined in the labs to check the ICP and to check the constituents of the clay. It was the clay was ground and crushed in the lab, and was allowed to flow through a sieve of number 200, so that we make sure we have a constant size of clay all over our experiments. And we used a weight of 20 grams of clay. The cation exchange resin was also obtained from a chemical lab, and it was R21 sodium plus. The constant weight of cation exchange resin maintained through the experiment was 50 grams. So we use clay 20 grams and manganese 50 grams. We used the volume of 1 liter of distilled water, and we prepared the samples with the different concentrations required, and we allowed the water to flow into bottles, and then the bottles were taken to measure the effluent concentrations of iron and magnesium after experimentation. Several parameters were tested through timing and percentage removal for the different concentrations. There were several parameters that were kept constant during performing the test. For example, the experiment was executed at atmospheric pressure. The temperature was maintained at 22 degrees. The flow was maintained in the range of 10 to 12 milliliter per minute. And the weight of the material used for clay and cation exchange resin were 20 and 50 grams respectively. 3 phases of the experimentation were performed, and the results were as follows. For phase 1 of the experimentation, it was the first thing was it was important to detect if clay and manganese would work out. Would work out to remove the ions of iron and manganese from water. So this was our main and prime concern, to test their applicability. So the results here we shows that within a time frame of we took samples after 30 minutes, then 60 minutes, then 90 minutes for iron. The solid line represents the iron, and the dotted lines represent the manganese. So as you can see here, the initial concentration of iron was around 55 milligrams per liter. The effluent, so as we can see here, the effluent of iron after 30 minutes decreased to 20, all right, and then to around 5 milligrams per liter. After 60 minutes, the concentration of iron decreased to around 22, and then to around 9 milligrams per liter, and then after 90 minutes it decreased again. But as we can see that the removal ratio as we go with time starts to decrease. So the effluent from after 90 minutes is higher than after 60, higher than after 30, which indicates that that the ions, that the void ratios within the clay ions have been compressed with the iron ions, so there was no more space to remove. Okay, this information is important. So if we want to implement this in real life, so we have to know for how long the clay material will bear or will remove iron, until which point, and then we have to like rewash it to remove the iron ions absorbed within it, so we can use it again. Also for manganese, the initial concentration here was 51 milligrams per liter, and with time, again after 30 minutes, it was removed. The removal was okay, but still high. After 60 minutes, the performance decreased, and after 90 minutes, we have a very bad level of performance or removal rate. So indicating that clay with manganese, the results weren't really very promising, like the removal of clay for the iron ions. So at least, but from this stage, and also we have to consider that we have started with very high initial concentrations, which is really higher than what we found in reality, or what is present in reality. But at least this phase of the experimentation proved to us that clay could remove iron and manganese ions. Whether we change in the criteria or the time duration or the setup of the experiment, still this material can remove iron and manganese. So our second phase was to detect the time required, the best time required in order to remove these heavy metals. So as we can see here, we have the effect of removal of iron, of clay and cation exchange resin on iron, with the blue line here for iron, and the one with the circle. So these two lines represent the removal of iron over time, all right? And the second two lines represent the removal of manganese over time. So we can see here that the best removal rate for iron was within the first like 10 to 20 minutes, and then the removal rate remained constant. Likewise, for the cation exchange resin, this was for the cation. For the clay, its efficiency went on increasing until 70 minutes, and then it started to slightly decrease. So the performance of clay here was or the operation of clay was for a longer time. It took longer time for clay to act as an absorbent material compared to cation exchange resin for the iron, for the removal of iron. For manganese, however, we find that the removal for clay here was decreasing dramatically, which shows which supports the first phase of the experiment, which stated that the performance of clay in removal of manganese was poor compared to cation exchange resin, which almost remained constant over time. And then from this stage, we went into to phase 3 of the experiment, where we wanted to study lower concentrations of iron and manganese of 10, 5, and 2. So we get closer to those detected in the groundwater here in Egypt, in the different governments, as stated at the beginning. So we started with the 10, and we examined the 10 and 5 and 2 ppm concentrations of iron. This whole figure represents only iron. 3 different concentrations using clay and using cation exchange resin. The solid lines represent the case of clay, and the dotted lines or the dashed lines represent the case of cation exchange resin. So as we can see that with time, I mean, the same duration as in the previous, as in experiment number 1 or phase 1 of the test, around 70 minutes was required to reach a maximum removal rate for iron, and we have maintained to reach the allowable limits for the 5 and the 2 ppm. So with initial concentrations of 5 and 2 ppm, we managed to have an effluent that would comply with the requirements of the Egyptian code and WHO. But however, the performance of cation exchange resin was poorer with iron at this stage. So we can see here that the 10 decreased, for example, to 2, but still yet started to increase. So the minimum effluent was 2, which is higher than the allowable limits. Also, for the 5 and 2, still the performance was quite a little bit far, better than before, but still still surpassing the limits. So we see here that the experiments show the positive application of clay in removal of iron is very clear, and it could be used to reach the allowable limits with low concentrations of iron and magnesium. And this here, we show the comparison of the removal rates. Again, for the 10, 5, and 2, for the 2 milligrams per liter, we have maintained to reach around, it was not detected in the effluent. Iron was not detected in the effluent, so it was around 100% removal. For the 5 milligram per liter, removal rates were around 89% after 60 minutes, 95% after 70 minutes, and 93% after 80 minutes, which again would be very promising with low concentrations of iron. For the 10, again, the initial was quite high, but 70%, 86, and 85 removal percentage ratios were achieved. Again, here, if we compare this is for clay and this is for the cation exchange resin, we see here that the effluent in all cases is much lower compared to clay. So again, all the 3 phases of experimentation have proven the very promising result of using clay, of Montreal clay structure, in the removal of iron ions. When we compare, so this was for iron. Now for manganese, for again manganese, we used 10, 5, and 2 milligrams per liter at the initial concentrations. Again, we have here the solid lines representing the effect of clay, and the dashed lines representing the effect of cation exchange resin. So if we focus at the bottom line, we see this brown line represents the limits, okay, according to the Egyptian limits required. And we can see that the effluent from cation exchange resin complied with the allowable limits. So the cation exchange resin had a very promising result in removing manganese compared to iron. Iron, it is true, it did remove a lot of the manganese, but still it did not manage to bring it to below the allowable limits, except for the 2 milligram per liter. We can see just met the limits after 20 to 30 minutes. So, and again, we see here that the effect of removal of cation here is reached almost 99 and 98% for all 3 cases of magnesium, which shows that it has a very promising effect in absorbing the manganese ion compared to iron, and has a higher effect compared to clay. Clay, the maximum that removal ratio attained was around 88% for all 3 concentrations, for the 10, 5, and 2 ppm concentrations of manganese. So in brief, we can say that the work here shows that clay and cation exchange resin both can remove iron and manganese from aqueous solution. However, clay minerals have a space between the layers which was able to absorb iron much better compared to manganese and for a longer duration. The cation exchange and the removal ratio attained was between 70 and 100% for the different concentrations of the 10, 5, and 2 ppm. And around 88% for manganese, which is still not a bad number. It is but still it would require more work or more concentration of cation exchange resin to achieve the allowable code limits. Cation exchange resin performed very well and very promising with manganese compared to iron, where for manganese it did achieve around 95 to 100% removal compared to iron. So this was in brief, Yani, the work performed and the paper which we worked and the results attained. Thank you for your attention. I hope I was in time.